Hello everyone, welcome to Computer Science E7. This is lecture 6, the histograms. So we've gotten all the Monday holidays out of the way, so we're in it for the long haul now. So now though we get to really get into what I think is actually the best part of this course, because before it was sort of the fundamentals of photography. You can think of it. The first half of this class is really meant to get everyone on the same page regarding really important photography terminology and exposure. I mean, this is some of the fundamental stuff. And so I know that I've been going a little bit fast through some of this stuff, and I apologize if it's a lot of bit fast. But now that we're getting to some of the good stuff here, hopefully we'll be able to slow it down a little bit and talk about some of this stuff as it pertains to digital photography, which is presumably why all of you are here. So today we're going to be talking about the histogram, and as you probably or you might know, most digital cameras, if not all modern digital cameras, have the ability of showing you a histogram. And you might wonder what on earth we can talk about for 2 hours about a histogram. But we're going to be laying even more fundamentals down that we're going to be using throughout the rest of this semester. And so there's going to be a lot of good stuff when we're talking about it today. So a histogram, what is it? Anyone know what a histogram is? Any math majors from back in the day? Histograms.
It's a graph that shows ranges of information.
Right, good. So it's a graph that shows ranges of information. So a histogram is not photography specific. It can be very, very general. So for example, this is a histogram of black cherry tree height. So basically what it shows you is it's showing you a count of information. So how much of something that exists. So in this case, there's a height for black cherry trees. They range from about 60 feet to 90 feet tall. And then it shows us on the y-axis the count of how many trees actually exist at each of those particular heights. So as you can see, we have about 3 at height 60. So in the range of 60 to 65, we have 3 trees. 65 to 70, we have 3 trees. 70 to 75, we jump up to 8 trees, so on and so forth. So unfortunately, I have to show us this somewhat, this is not a very relevant histogram. Back a couple of years ago when we first started doing this class, this lecture, the histogram, came right after the exam lecture, and we had a really nice histogram of how everybody did. And it tended to be sort of like this, right in the middle. And no, I'm kidding. They did very, very well. But basically, now we have to show this sort of irrelevant one, really. But this really, it just shows a frequency of how much of something there exists. So the ones that we see in digital cameras are maybe, they look a little bit more organic in a way. There's much more data that's visible within them. There's a much finer grain amount of detail. You can see that if you look closely, there's individual bars still, but it looks a lot smoother when we look at it from far away, as in this slide, or as on our cameras, or even in Photoshop, for example. But basically, this tells us some very important things. So along the x-axis, we have a range of basically darkness, so dark all the way to white. So we have at the very far left at the end the amount of black that exists in a photo, and all the way at the far right the amount of white that exists within it. And then as we get within a range somewhere in here, there is a count. So the higher the bar in that particular range, that means the more of that one specific tone there is. Now, you might think right here, okay, this seems like a really good place to stop, because that's a histogram. I've explained it, and now you can look at a histogram and kind of say, okay, well, it should sort of be right in the middle, because you don't want a lot, in the very dark region. You don't want a lot in the very light region, or you could be under or overexposed, respectively. But there is a lot more detail that can be said about this. So first of all, the amount of information that exists between here and here, it's not just black and white, obviously. There's a bit of gray in here. And this gray that exists, this gradual change, is basically the tones that exist within the image. And so we have a couple of really important concepts that are come into play here. So we have one concept called dynamic range, and then we have another concept called tonal range. And dynamic range is basically I'm just going to introduce it quickly now, and we'll talk about it more at the end of the lecture. It's basically just the difference in dark to light that we can get. So basically how many stops we can capture in an image. So if we have very, very wide tonal range, then maybe we would be able to get more details in the shadows or in the highlight of a very difficult scene. For example, if there's very, very harsh sunlight, as you might know, you get very bright light on the face of a person and you get a very harsh shadow. A better dynamic range means that you'll be able to preserve details in the very brightest and the very darkest regions. If you have less dynamic range, then it's going to become overexposed much more quickly in these difficult situations. Now, tonal range, which is much more important to us when we're talking about histograms, is basically the amount of gradation that we have in the middle here. So how many tones we have from this deepest black to this brightest white. So if we have a wide tonal range, then we could have these very smooth gradients, as if we have just a picture of something that goes slowly from black to white, for example, it would look very smooth. There's not this sort of a step that you would see as the brightness level goes from dark to a little bit brighter to a little bit brighter. It will look a lot smoother if we have a larger tonal range. And that's something that's very important to keep in mind as we move forward. But okay, let's go back to histograms here. So what I'm telling you about histograms is that it's just a frequency count of basically the tones within an image. So if you have, in this case, in this histogram's case, you can see that we have a very high amount of tones in sort of this mid-bright region. So not right here, not right in the middle, but it's sort of middle bright, which actually would be pretty good. But if we take a look at some real-world examples of histograms, for example, a total underexposure, where we just completely messed up, or we took a photo with the lens cap on, or something like that, and it was a completely black photo, then what you would expect to see is this. You have nothing that's brighter than completely dark, but you see just this very tall, sort of black column that exists at the very left side of the luminosity. Now, you can imagine what happens if we have a total overexposure. Let's say that we were using the manual mode and we were taking a night scene, for example. So we have a really long exposure, maybe low ISO, so on and so forth. Then we put the camera away, then we come back the next day and take a photo with the same settings, forgetting that we had used those settings, and it's completely white. What would the histogram look like in this case? Yep, exactly. So we have a bar that's completely on the right. Now, obviously, this is not going to be the general case for photographs. You're not going to have one color, one tone that's going to be completely white or completely black. And in fact, I should mention that this is just a window taken basically from Photoshop. So if you have seen a histogram on your own camera, rest assured that what we are talking about is important for not just that, but also for some of the tools that exist for your computer today. But going back to these photographs, this is generally not the type of photograph that we take for artistic reasons. So what we might have is something much more like this. So this was the pinhole photo from last year, but it shows, the whole point of this is that we have the photo and then the histogram right next to it. It shows us the histogram that exists there. Now, one thing that's really important to mention about the histograms is that when you take a photo, generally you're chimping over your camera to take a look at what the photo looks like, and you're looking just at the photo. Now, this can be very, very deceptive for a variety of reasons. One of them is that the LCD on the back of your camera is not going to do a very good job of showing you just how light or just how dark that is, depending on the lighting conditions that you are in. So for example, if you are outside, it's really bright, really sunny, most likely your LCD is going to be washed out and it's going to be difficult to tell just how bright or just how dark that is. And on the other side, if it's completely dark, then what can happen is that it will look brighter than it actually will once you put it onto a computer, for example. And so this is a very bad combination. When you're in the dark and you're looking at a photo and it looks brighter, then you might say, okay, well, I'm done, but you're really not. It actually was much, much too dark. It was very underexposed compared to what you want. And so this is where the histogram can come into play, where you can try to fit the tones within the photo into sort of the center region of the histogram. Now, what I'm trying to show you here are some well-exposed examples of what a histogram would look like, but you will see that there's not one sort of formula that a histogram follows in order to be correct. So this one's very easy. There's all of the tones fit within the dynamic range of the camera. There's nothing that's brighter than the brightest white that the camera is capable of taking. There's nothing darker than the deepest black. And the reason that I know that is that all of the tones, as shown by the histogram, fit within the histogram. There's nothing at the far ends, as we would see if if there were some pixels that were completely overexposed, we would see a little bump all the way on the right side, and vice versa for underexposure. Okay, so keeping that in mind, as we look through some more examples, here's one where the dynamic range of the scene is perhaps a little bit wider. There's a wider change in the amount of brightness or the amount of light in a scene, and so we have then a wider histogram that exists. And one of the things that you'll notice, though, about this histogram that might be tricky is this hump down at the very far left end. It looks predominant. You might look at this, and if you were looking only at the histogram rather than at the image itself, you might say, well, this actually could be a little underexposed because the majority of the pixels that I want are at the far left end of this histogram. But that shouldn't fool you, and I'll explain why in just a little bit. Now, is there anything that's pure white in this scene? Yeah, sure. So yeah, right here we have the t-shirt. There's a little bit of overexposure there, so we lose some of the details. And even though, as we saw a couple of slides ago, that total overexposure would show us a big spike on the right side, even though we do have some overexposure in this image, it's really tough to see. There's a little tiny blip that's over here. And in fact, the blip that you're seeing probably isn't even it. There's a smaller one that's right next to it that represents that overexposure. And so sometimes cameras allow us an additional opportunity to see overexposed regions. Sometimes it will flash overexposed regions in a different color, like red, or usually it's bad if they do it in a color, because that's if you overexpose just red, for example, then you don't see it flashing, so it's kind of silly. But if they flash it in black, for example, then you would be able to see that that particular region is overexposed. And in a scene like this where there's a lot of light, you're probably not going to be able to do anything to get a better exposure, frankly. If you wanted to decrease the exposure value so that this was then less overexposed, right? You turn down the exposure value so you can get it to be better in terms of the exposure, then everything else could look underexposed. Okay, so let's take a look at a few more examples. Here's another one that we've seen before. This has quite a large dynamic range, this scene, because as you can tell, we have quite a few regions that are very, very dark, particularly the upper left-hand corner, and then we have some regions that are completely white, so as in right here above where a light was, just underneath the waterfall. And that's reflected in the histogram. We have a very large spike here along the left and just a little bit of white along the right side here. Now, so remember that no one histogram formula makes it right. So each of these could be considered well exposed, and the histograms, as you can see, vary by quite a large margin. So you can't just look at just the photo on your LCD screen. You can't just look at the histogram. You really need to look at both and try to make a determination of the exposure, of the final exposure of your scene. Now, one of the things that's important to realize is that the histograms that the cameras show you and that your computers show you are a fixed height. They don't get any higher, they don't get any shorter than the height that you currently see. So right here, I have this very, very big spike, and it has to fit that spike along with these other sort of valleys or these other peaks and valleys that exist within the histogram onto that same height. So what the camera does is it will tend to shrink the histogram. It will just compress it down a little bit. It won't change the width at all, but it'll make it a little bit shorter, or it'll make it a little bit higher to try to make it a little bit more apparent what some of these histograms are. And that was sort of the problem that we saw here. We have quite a few pixels that are a little bit darker, which is sort of the background region that exists here. And even the shorts and the shadows, there's a variety of regions in here that are darker. But it doesn't contribute to an overall underexposure of the image. And so once you realize that once the camera or the computer calculates the histogram and it changes the height to fit in that fixed height histogram window, then hopefully it will make a little bit more sense that, sure, this might have been stretched up a little bit. So, well, keep in mind that everything gets stretched the same amount. It doesn't change the height of each, because then it makes the whole histogram useless, really. So all of this stuff could be stretched up. So it looks like there's more area under this graph versus this, for example. And the reason is that this one black bar that represents this complete underexposure in this photograph is taking up most of the height, and everything else has to be shrunk in comparison. And so this can be confusing, particularly when you are intentionally forcing an underexposure or an overexposure, as in this case. So in this case, the majority of the pixels are black or very, very close to it. And even though there is a considerable portion of the image that is properly exposed, the histogram is going to sort of fake you out. You'll only see a little bit of a blip. As you can see, there's a little bit of a hump right in sort of the middle of the tonal range that represents this properly exposed portion of the photo. The majority of this photo is black, so it's going to be represented by this far left area of the histogram here. And similarly, for complete overexposure, we have this, where we have this very, very large overexposed region, and we have just sort of a very small hump in the middle of the histogram. So if you are intentionally trying to force an overexposure, this could be something to watch out for. But if you are not, if you're just trying to regularly expose an image, then you should look for a very, very sharp spike on either end and try to adjust accordingly. Now this is sort of the pitfalls of the histograms, but keep in mind that this is really, really useful to us. So for example, we have this snowscape shot that I showed when I was demonstrating the exposure values, or the exposure compensation rather, from a couple lectures ago. Now, when I first took this photograph, it was getting sort of dark outside, and I looked at the photo, and it looked fine. And this was that problem that I was telling you about, where it's somewhat dark outside and the photo looks brighter than it does. Well, this looked white enough to me that I said, okay, that's it. And I actually left this scene before I said, maybe I should check the histogram. So while I was about a block away, I realized that the histogram was way down here, indicating that the majority of the pixels are actually quite underexposed. And so I had to go back, walk all the way back to this stupid place, take a photo, and it's not even that interesting of a photo anyway. It was a big waste of time. But anyway, it wasn't a waste of time because I get to show it to you and use it to explain. But anyway, so now after you force this overexposure by increasing the exposure compensation by about a stop and a third, as was the case here, then you get a more properly appearing histogram. So especially with snow, you want a histogram that leans primarily to the right end of the spectrum, because you want a lot of that white snow visible in it. You don't want to go too far. If you go too far, you'll overexpose some of these pixels, but there's a little bit of a gap here, which shows you that you will have some values that exist within these white regions in the snow, and you'll be able to see all of this information a little bit more clearly. All right, now I have to embarrass myself once again and show you this awful photo, where you remember that I pretty much completely overexposed the sky and then completely underexposed the bridge. And if I had bothered to look at the histogram at the time, well, I mean, it was obvious also from the photo when I just took it. But when you take a look at the histogram, it does become very obvious the problem that exists, and that is that the majority of the values are just so far off to either end of the histogram that the dynamic range of this scene is just far too wide. It's just too much, there's too much variation in the brightness of the scene for my camera to be able to get it. All right, this is easy, right? Piece of cake. Now you're saying, okay, you know, before you faked me out a little bit when you said that, you know, that's sort of the end of all the stuff that we had to talk about with histograms. Now I could do it again and say, okay, well, we've got into more detail about histograms, and that's it. We could pack up and go home. But the problem is that the devil is in the details. And so we have to go back to this lovely slide from the first lecture, and this is where the digital aspect of digital photography is really going to come back into play. So bits and bytes. So a bit is 0 or a 1. It's the language of computers and digital cameras, so to speak. And a byte is just 8 bits. And this allows us to have 1 byte represent so many different discrete values. So if we have 8 bits, how many different values can we represent with it? So more than 16. And the reason is that just like we have when we are talking about our own counting system, where versus binary, which goes from 0, 1, and then, let's see, let's do this, and then 1, 0, where we count from 0 through 9 before we go to the next place. So if we have, let's see, I'm trying to figure out how I can make this, explain this more easily. But let's say we have the number 128. Now we know what this is intuitively because we've learned how to count in base 10. But if we go back, and I'm not doing this to try to say that you all are stupid, because I know you're not, but I'm just trying to break this down for you. We have, and this is going to sound very elementary, but we have 3 places. We have the hundreds place, right? We have 100, and then we have a tens place. We have 2 of the tens place, and then we have a ones place. Now, when we have 3 places here, we can represent how many different numbers when we're thinking about the decimal system. So if we have the ones place, the tens place, and the hundreds place, how many different numbers can we represent? We have 0, 0, 0, that's 1, 0, 0, 1, that's 2. 999, well technically 1,000 if we include 0, right? Okay, now keep this in mind when we're talking about binary. Now binary looks like this, but it has the concept of places as well, but it's just a little bit different. So we have a ones place, oh boy, this is going to get confusing, a twos place, a fours place, an eights place, a 16s place. And what ends up happening is that when you figure out that what you did up here was basically you did, okay, well the ones place can have 10 different digits, the tens place can have 10 different digits, and the hundreds place can have 10 different digits. You figured out that, okay, when I have 3 digits, I can have 1,000 different values. In binary, when I have 8 different digits, it's 2 times 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 2. That's 8, so that's 2 to the 8th power, which is 256 unique numbers that can be counted with 1 byte. And you can, if you want to convince yourself of this, you can go home tonight and you can start from 0 and count in binary. 0, 1, all right, 1, 0, okay, 1, 1, and then 1, 0, 0, and then 1, 0, and keep going and going and going. You will figure out that you have 256 different values. Okay, now, it's possible to convert numbers from binary to decimal, but I will spare you of that horribleness. Okay, now, when we are talking about bytes, remember that we said that there's different file types that exist, and one of the predominant file types is JPEG, and that has so many bytes attributed to it. So does anybody remember anything about the JPEG file type? It was how many bits could we store? We said it was an 8-bit file type. So that means that each color could have 8 bits of information. So we could have 256 different values for red, 256 different values for green, and for blue. Now, the same sort of thing happens with histograms. The histograms are computed based on a level of black to white, where black represents the value 0, and white represents the value 1. Now, what's important to realize is that these histograms that we've been looking at don't talk about color. It's just talking about black and white. But there's an inherent problem with converting black and white to color. And in fact, there's a couple of different ways that we could, well, no, I said it backwards. There's an inherent problem in calculating, did I say it right? Calculating black and white from color is what I meant. I don't know if that's what I said. Okay, but anyway, so we have 256 different values that we can deal with, and we have to try to convert this color down into it. And so, as you recall, we have the JPEG file type, where each color can represent 8 bits of information, so 256 different values of information. And so to make that a little bit more concrete, if the red section is 0, then there's a complete absence of that color. If the green section is 0, there's a complete absence of that color. If the blue section is 0, there's a complete absence of that color. You add those 3 up, and it's just black. There's just no color at that region. But if we do the opposite, 255 plus 255 plus 255, this represents white. And so we can even get all of the colors in between. So if we had the complete presence of red, so 255 for red, 0 for green, and 0 for blue, what color would we get in the end? Yeah, just red. So we could do the same if we had 0, 255, 0, we would have just green, so on and so forth. And we can combine these. So if we do 255, 0, 255, we would expect a bright purple, sort of it's a bright purple rather than a violet, and so on and so forth. Then we get this entire gradation, all of these changes in colors that exist because of this. So we could add blue and green. So if we had 0, 255, and 255, what do you think the color we would get is? That was grammatically terrible, but what color do you think we would get out of that? Yes, cyan. Perfect. All right, so blue plus red is sort of like a violet, and a red plus a green. So 255, 255, and 0 is a yellow. And so once you start to understand this, hopefully a lot of these other aspects of computers will start to make sense. So you might have seen something like this. So this is Photoshop's color picker, where you can pick a color among all of the ones that are available to you. And so just to give you an idea, if we have 256 values for red, 256 values for green, and 256 values for blue, how many different colors could we get out of that? So yeah, it's a lot. So it's basically, it's 24 bits of information, and that is going to be something like, what is it, 16 million, I think, or something like that. It's a lot. It's a lot of colors. So rest assured, I don't even know. I can do 2 to the 24th in my head. I'm not that good. So there's a lot of colors here. Now, what we could do is use this color picker to try to figure out different colors. So what we were talking about before was doing, let's say, 255 of red, 0 green, and 0 of blue. Keep in mind that there's a lot of other ways we can compute colors, but we're dealing with this RGB section here. And you see that the end result color at the very top is this red. And so we could do the same. Now, and I'm just using these extreme examples just to show you, very concretely how we can mix some of these colors. But usually what we see are variations, or all of the intermediate values that exist between them. So here I've combined about halfway, about half a red and half a blue, so we get this sort of deep violet color that exists out of it, versus a complete, oops, no, I think it gave me an error here. Okay, here we go. Rather than doing something like this, which is a much brighter purple. Okay, but going back to this. All right, so we have all of these colors, but as you've seen, histograms typically don't show you this color information. It's this black and white information that we were talking about. Did you have a question?
Yeah, I was just wondering, so then if you shoot digitally in black and white,
Mm-hmm.
you're losing a lot of information.
Yeah, that's right. Yeah, when you shoot digitally in black and white, you are throwing away all of the color information that exists. So you're basically going from having three 3 bytes of information per pixel because you have 1 byte for red, 1 byte for green, 1 byte for blue. And you're just replicating all of that information at every pixel. So if you make all of these numbers the same, so for example, 128, 128, 128, you just get this sort of boring gray color. And as you increase all of them or decrease all of them at the same time, it's just the various levels of gray that exist. So when your camera is taking a black and white photo versus you taking a color photo and then later converting it to black and white, you're just throwing away 2 other pieces of information. You're just basically making it just this luminance or just this, this amount of brightness that exists within the scene. So very much like digital zoom, I don't recommend you take photos in black and white on your camera. Just do it later if you want to do it. You have more options at the later time because, as we'll talk about in the color lecture, it's more complicated than just converting a photo to black and white. There's many options available to you, especially when you have that color information available to you. And as a teaser to that, and one of the things that's important to us is this discussion about how a histogram converts color, this color information, red, green, and blue, to this grayscale, to this black to white range that we were talking about. So how do we do this? How do we convert this change of color to this grayscale? To do that, well, okay, actually let me ask you, so what would a reasonable person do in this case? If we had 3 pieces of color information, we needed to just make 1 piece of color information, how would we do that? We could just average the red, the green, and the blue, for example. And then we would get something that looks like this, just this sort of dull gray color. Okay, but in order to figure out how we actually do this, we have to take another step back to the very first lecture when we talked about the eye. So now you can see that all of this stuff where I'm always, before I was always punting it off like, oh, we'll talk about this later, we'll talk about this later. It's starting to come together now, and it's a very exciting time for us here at E7. Okay, now the eye, we were talking about the rods and cones that exist within the eye. So if you remember, the eye is in the center of the eye, at least the color information is provided to us by the cone cells. And there's 3 different types of cone cells, but primarily we have the M and the L type cone cells in our eye. So we have the majority of the cone cells consist of the M and the L type, and the minority consists of the S type. And I believe that the average person, this doesn't mean that, I think when they say average, they just mean the average of all people rather than, you take somebody randomly and that's an average person. The average person will have 98% M and L type and 2% of the S type. So this is a very big change in, excuse me, in the number of cone cells that we have. Okay, so I have an activity for you. So this is, again, we're going back to elementary school and we have to do something like the teacher says, okay class, now everybody do this. So I want you to close your eyes for a moment. Don't worry, I'm not going to do anything silly like start throwing stuff at you. And close your eyes for a moment and imagine that you have 3 rooms. They're all completely dark, and then there's a light switch. Okay, so you flip on this light switch, and each of the 3 rooms has a different color bulb. Room A has a red bulb in it, and it completely illuminates in red. Room B has a green bulb in it, so it's completely illuminated with a green light. Room C is a blue light. Now imagine that they're the same intensity, it's the same amount of light in both rooms, in all 3 rooms. Which room appears the brightest? When you go in, which room can you see the most in? Green, right, and that's exactly right. And that is because of the cone cells that we have in our eye. We are tuned, for whatever reason, most likely evolutionarily, that we are tuned to be able to see large gradations in the green color. And that is reflected in the fact that we have the vast majority of cone cells in our eyes are the M and the L type, which are stimulated mostly by green and to a lesser extent, but still to an extent, by red light. And blue light is all the way back here, detected by those S cones, just because it is a short wavelength. And in fact, that is exactly what appears to us in our eyes. So if you sort of imagine each of these is converted to grayscale, this should look kind of approximately right in terms of how bright this color is, how bright this color appears to us. The green is by far the brightest. Then there's the red, which is still kind of bright, but a little bit darker. And then there's the blue, which even though it is the same intensity as the red and the green, it is considerably darker to us. And if you're familiar, I don't know if all of you went through this, but when I was in elementary school, they had us do these hearing tests. They put us into this room and they put a large headset on us, and they would gauge our response to various frequencies, like to determine how tone deaf we were to various frequencies. And you could always tell which ones were just very, very hard to hear. They were so faint, even though they were probably at the same intensity. And it's the same sort of thing. Our ears have different response to different frequencies of sound, and our eyes have a different response to different frequencies of light. So this is very, very important to us when we're talking about luminance detection, or the brightness detection of a color, when we're trying to convert it to black and white. And we can actually quantify this into an equation. And in fact, that is what we do when we're talking about luminance. Yes, it's funny because there's more equations here, but this is important to us when we are calculating a luminance histogram. So a luminance value is made up by 30% red, about 60% green, and about 10% blue. So on a scale of 0, which is completely dark, and 100%, which is completely light, this is about how much each of these colors appears to us in brightness. So 60% is to green, so the majority of the brightness comes to us by green. Then half of that is red, and then poor old blue over there has the short end of the stick, so to speak. So we can then say that the green is twice as important as the red when we're taking color into account and converting it into black and white. And it's important that I'm talking about luminance. I'm talking about the apparent brightness of a scene and not any other type of black and white. So there's other ways that we could compute black and white from color, but I'm just talking about how we perceive the scene in terms of its brightness. Okay. And if we start bringing color into these histogram calculations, this should hopefully make a lot more sense. So when we see something that is only red, for example, it doesn't look very bright, not as bright as white, not as bright as green, but it's only sort of bright. And so if we have a photo that is only red, then we get this spike right here at about 30% of the way over in the histogram. Now, I should mention that whereas before we were talking about using just an average to try to calculate the histogram from the color information that we have, it still works out that we have an equation that looks sort of crazy like this. And the reason that this works is that these three numbers add up to 1. So what happens is that when we multiply, no matter what these numbers are within the range of 0 to 255, these numbers can be any number within that range. And when you add them all up, it will always be another number from 0 to 255. So you're not going to get more than that. You're not going to get less than that. It's always going to be somewhere right in the middle. And it works out. If we think of, if we have all red, so 255 red, all green, 255 green, and all blue, 255 blue, we expect that to be white, right? We were talking about mixing those colors, and we get white as the result. So if we did that, we get what for our luminance calculation? So you could actually do the math and figure out that, all right, I'll do the math. We could simplify the equation and make it a little bit easier, but we could also just do the math and make it a little bit easier. So let's say we said we have 0.3 times 255. So that's about 77. Okay, then I have, let's see, 255 times about 0.59 or about 0.6. That's 150.45. Okay, then I have the blue, 255 times 11%, 28.05. Now if I add those three together, you see that I get 255, which makes sense. So this equation still makes sense. Even if we have the complete presence of all these colors, which represents white, the luminance calculation still shows us that it is bright. It's fully bright as we would expect it to be. And similarly, it should hopefully be easy to figure out what 0 would be. It's just 0 plus 0 plus 0. So the luminance would then be 0. So here, when we talked about using the total presence of one color when we're trying to calculate one of these histograms, and we have red right here. Now remember that I said that if it's all red, it's 255 times 0.3. If you remember, it was about 77. And if you take a look at the data that exists here, you see that's precisely what this shows us. The average amount of data in this histogram is 76. The median is 76. The level is 76. That's because all of this information is right here at 76. And so this is proving my point where I said that we have complete absence of brightness here at value 0. Then we go all the way across to 255. That means that all these intermediate values are represented by the color. So at about 30% of the way, or a value of 76, we have this one large spike in the luminosity histogram. Okay, so what would this look like if it was all green? How would the... Yeah, so it'd probably be like about right here, about 60% of the way over. And how about all blue? All the way right here, something like right there, about 10% of the way over. And again, if you don't believe me, you can actually open up a, you can go into Photoshop and just open any old object like this or any old document and then actually use, let's see, I said, let's try blue. So I'm going to pick an all blue color down here using the color picker. Okay, click OK, and then paint bucket it in. Now if I show you the histogram over here, hopefully I'm not going to embarrass myself. You'll see that it is exactly 10% of the way over. Okay, that's pretty cool. But one of the things that's really cool is if you were ultra nerdy, more so than me, and you actually try to make, okay, so imagine this. So you've seen how we can try to figure out a way that we can paint color into an image right here, and then actually show as a result some known spike in the histogram. So imagine you took that a step further and you tried to make an image in the histogram based on the values that you put here. And that is exactly what this one guy did, which is really awesome. He made this histogram right here, which is the old New York City skyline. And the image that made that is this gradient right here. And if you look at it, you'll actually be able to see that there's varying amounts of color. And actually, you'll also be able to see that there's, even though this is a grayscale, it's a grayscale gradient. In other words, it goes from black to white and the values in between. There's not supposed to be any color. You can also sort of see that there's like a kind of a green tint to it here. This is a good precursor to my big rant in a couple of lectures about properly calibrating the color of your monitor, because it will show you this color improperly. Okay, but getting sidetracked here. So now, if we look at this gradient, you'll see that there's varying amounts of each of these colors, and he was actually able to use that to his advantage to create a gradient like this. So it's pretty cool, and it's definitely a pretty good read. And if you really wanted to, you could copy this into Photoshop. It's very meta something. It's pretty neat. Okay. Anyways, back to this. Making our own histogram is one way that we could try to figure out how to do this. Now, I'm not going to show you all a photo and say, okay, let's build a histogram from this, because that would be terrible. We'd have to take every pixel, calculate the luminance at every pixel, and then build the histogram from there. But I still am kind of mean, so let's try to figure out what the histogram of this would be. And so if we're just talking about this conceptually, and rather than each of you pulling out a piece of paper, because we're not that elementary school here. So if we have this image in Photoshop and we wanted to know what that histogram would look like, how would we do this? Well, first let's think about it this way. Which spikes would be the tallest? Yep, so these primary colors, red, the green, and the blue. How much taller would they be? Yeah, so they'd be twice as tall. So we have some spikes. We have 4 spikes somewhere for these colors. They're a certain height. And then we have twice as tall these other spikes for this color information. And so, because remember these histograms are a fixed height, we can imagine that these tall spikes are going to take up the entirety of the histogram. Then those half spikes will be exactly half of it there. So we have a couple of easy ones that we could try to knock off on our histogram. And just temporarily I'll try to, I know this will be tough to see, but I'll show you more concretely. This is just so we can write it down on the blackboard for now. So let's just try to get some of the easy ones out of the way. So what are some easy ones we can do right now? The white and the black. Okay, so we know that those are half height, and the black one will be all the way back here. The white one will be all the way up here. So I'm drawing multiple lines, but I'm just trying to give it thickness rather than trying to imply that it's wider. Okay, so what other ones would be easy? Yep, okay, so the red, the green, and the blue. So let's do it in the reverse order. Blue, which would be, yep, so about 10% over here, and it'd be the entire height. How about green? Yep, 60% over, so not all the way to the right, but almost. So about there. And then we have red, which is 30%, so it's about there, something like that. Okay, now we have these 2 other colors, which are a little bit more complicated, a yellow and a cyan. And I sort of gave these answers away earlier when I was talking about combining these, so I hope you were paying attention. So how can we make these 2 last spikes on this histogram? So the yellow would be what? Would be halfway between the red. So why is that? Why would it be? So it's actually not quite. So if we keep in mind that yellow is made up of which 2 colors? It's made up of the red and the green, which means that if we have a yellow color, then we have the complete presence of that particular color, which means that we have 255 times 0.6 plus 255 times 0.3, and I'm just rounding here to make it easier. So that means we have 255 times 0.9. So this is going to be about 90% of the way over. Okay, so we have another half spike that's about here. So this yellow one is brighter. It's brighter to us, but it is also brighter in the luminance calculation than any of these primary colors. That's what this should be telling you. Okay, so how about this cyan one? Which one is that? Yeah, blue and green. So we have 0.6 plus 0.1, so we get about 70% of the way over. So we have a little spike that's just a little bit to the right of our green one. Okay. That wasn't too painful, right? And in fact, it would have been a lot easier had we just put it into Photoshop in the first place. And you see that we get exactly the same thing that we just talked about. Pretty neat, I think. Okay. Now, yes, this is breaking it down a little bit much. But the whole point of this is to get you to understand what this is showing you. And secondly, that there is more than just luminosity. So if you remember, when I was over here in Photoshop somewhere, and at first it wasn't showing me the correct histogram, That's because there's a variety of histograms available to me. So the other ones aren't quite as difficult to figure out as luminosity. So we've gotten the hard one out of the way, but it's important to show the difference between it. Now, before we even get into that, imagine that we're talking about things that are just a little bit more photographic. So rather than having just these very big swaths of color that are, completely colorful and completely saturated, we have something that's a little bit more photographic, and this is a gradient. So you can imagine that if we have a red gradient from red all the way to white, it starts out red and it's getting brighter and brighter and brighter. And so that's the sort of histogram that we see here. Now here's a question for you. Why is it so jagged? Why does it go up and down, rather than looking sort of like a smooth amount? So first of all, I guess even before that, why does it go down and then come back up in this gradient?
Because there's more extremes on either end.
Right, that's right. So over here, there's a certain amount of width of pixels of pure red and pure white, and those are sort of the high points in this parabola of sorts. So if this gradient was more uniform, so if there was less of the pure red on this end and less of the pure white on this end, then it would be a bit flatter. But that's not the case. There's more red and more white than the gradient itself. So we see this sort of dip in the middle. Now we have this kind of crazy up and down motion. Why might that be? Any ideas? Okay, well, it is because and you can imagine that this is a gradient, but as it's being transformed, as it's increasing the amount of white, so as it's getting more and more white, there's more of some pixels than other. It can't be perfectly even unless it were exactly the width of let's see, it would have to be something like 65,000 pixels wide or something like that, and it would have to be exactly one value separated between each before you would get a very, very nice curved histogram. It's just the difference in the amount of values that you see. And in fact, Photoshop does a pretty bad job of smoothing out those histograms for us, and we see these sort of jagged histograms in Photoshop a lot more than we would in, say, our cameras, which try to smoothen them out a little bit to make it a little bit more legible, versus this, which I think is going for accuracy. Okay, now you can imagine that, I did mention that we have several different types of histograms, more than just luminosity. So hopefully this histogram makes sense to you. But what if we had a histogram that was just showing us the red color, only red? What would that look like? So it's a trick question.
It would be more sort of centered on this, or on the 30% left-hand edge.
Okay, so let me break this down a little bit more. Remember that a histogram goes from 0, the value of 0, all the way to 255. So if we had a histogram measuring red, then we're measuring the frequency of red pixels that are 0 to 255. So what could it look like? This is going to blow your mind. There's no angles, it is just a line. And the reason for that is that this is completely red throughout here. Remember, what makes white? We're adding more and more green and blue, which means that this has to be completely red on this end as much as this side is red as well. So over here on this end, we have not only the complete presence of green, the complete presence of blue, but also the complete presence of red. So even though this side isn't red, red still has to be here in terms of its values for it to look like this. Okay, so how about green then? Right, so here there's a complete absence of green, and then it goes to the complete presence of green. So we would expect it to be sort of a line. And remember that since we have this sort of buffer on either end where there's a little bit more red and a little bit more white on each end, we have this sort of curved down appearance. And so blue is actually a similar thing. So these histograms are very, very different, but they tell us some pretty important things, or some very interesting things at least, about this particular image. Yes? So I'm not quite sure I understand the question. You're not sure why there's so much green on either end?
Yeah, if the green and blue luminancy histograms are applied to that red gradient.
Up here? At the luminance histogram? Oh.
So the red gradient.
Yes.
And the green and blue are also measuring the amount of green and blue in that red gradient.
Right.
I can understand how there's a lot of green and blue value on the left.
Okay, so the color in this histogram is misleading. So keep in mind that at this far end, this means that there's a value of 0, which means that there's no green. So when this is giving you a bar right here, this means that there are this many pixels that have the value of green is 0, where the value of green is 0. So over here, there's so many pixels. There's a little rectangle of pure red pixels that have 0 green values associated to them, and that is what this is measuring right here. So what would be more accurate, perhaps, is if this itself were a gradient where it had the same shape, but the color of this shape goes from black to green. That might make a little bit more sense, but it only makes sense at first, only because once we know that that is how this is measuring those values, then it can become a little bit hairier if we have a differently shaped histogram. So it's better if we have a uniform color, at least for this particular histogram. Okay. Oh, yes.
Following up on that, if on the left side, towards not the far left, but maybe 10% over, there's some green value, some blue value. How come there's no?
Oh, so here, so in this left portion, there's some red, there's some green, and there's some blue, but there's no luminance. So remember, the luminance is showing us the apparent brightness of the image. And that is what that luminance calculation was all about. So there can be some values where there are no green pixels and no blue pixels, but because there are red pixels here everywhere throughout the image, this entire image has a certain amount of brightness to our eyes. And that is what the luminance is showing us. So if this was a black to white gradient, then the luminance would extend all the way, and so would each of these color values, just because in that case, at the black end, there's a complete absence of all of these colors, and at the right end, there's a complete presence of all of these colors. Now, it's conceptually difficult, and that is what this slide is trying to show us, is the difference between the luminance histogram and these other histograms that exist, is that there can be pixels where there's no blue and no green, and we can have this sort of unintuitive gap in the luminance histogram. It's just important to realize that the luminance is only showing us the apparent brightness. That's all the difference is. It's not some summation of the other values that exist in the red, and the green, and the blue. It's actually showing us the apparent brightness of that image. And so this can actually be detrimental, as we'll see in the second half, when we are trying to use the histogram to try to figure out if we've not only overexposed something, but more importantly, if we've just overexposed one particular color channel. So with that, let's take a 5-minute break, and when we come back, we'll talk more about the fascinating world of histograms. Okay, welcome back, everybody. So before we dive right back into histograms, just wanted to give out a quick reminder that the third assignment is coming out. It seems crazy that we're already halfway through the semester in terms of assignments. And it just seems like 3 weeks ago when it was still light outside at this point in time today. So it's a little it's a little depressing, but despite the fact that we have less daylight, you should hopefully still be able to get some truly excellent photos for this assignment. So, as with assignment 2, there are 3 parts to this assignment. The first is just a theoretical problem set-like part. Second part is primarily taking photos type part. And one thing that I do want to mention, so there's a few changes from the second assignment. Some of the types of photos that you'll be taking is slightly different, but also you'll notice that the technical requirements, though, while largely the same in terms of keeping your photos unmodified and making sure that you submit them in JPEG formats and you don't modify them, said that twice, so on and so forth, just making sure that's really understood. I do mention that you can start taking photos in the RAW format. And the reason for this is that you will probably want to start building your library of RAW photographs, because that way you might be able to start using them maybe for your final project. You could potentially use them for some of the questions that are coming in the 4th assignment. But it's still important that you realize that even if you do take photos in the RAW format, you don't have to, first of all. You can continue taking photos in the JPEG, and in fact, you must submit them to Flickr in the JPEG format. And the reason for that is that Flickr only takes JPEG photos. So if you do decide to take photos in the RAW format on your camera, I recommend the setting. Some cameras have a RAW plus JPEG option where it will take the same photograph and save it in both formats at the same time. Then that way you can just sort of file away the RAW format file, and you can upload the JPEG to Flickr. If you do decide to take photos in RAW and your camera only supports the RAW format, you'll need to process them into JPEG formats. You can either use the software that came with your camera or Photoshop. Just keep in mind to use the default options when you process it and submit it. You don't want to do too much of changing of that photo in software. Then, of course, the third part of the assignment is it's a similar thing as with last time, where if you're having a problem with one of the images, upload it to Flickr, and everyone else in this room will help you with that. And of course, I don't want you to feel like we're trying to force you to use the Flickr discussion board. That's not what this is about at all. What it's about is getting feedback on your photos and thinking critically about other people's photos. So this is one of the relatively few aspects, as you can tell from this lecture. It's somewhat technical, this material. And this is one of the few ways that we get to discuss each other's photos, maybe step outside of that technical aspect a little bit and talk a little bit about the artistic side of it. In fact, if you read the somewhat appropriate cartoon on the front, it's very much similar to that, where it's from this web comic that, especially initially, was really quite funny, called What the Duck, and it involves photography and ducks and what's not to like about that. So anyway, back to this. Of course, if you do have any questions, you can feel free to let any of us know. Now, I know that talking about some of this stuff is a little bit confusing, and you may be wondering why on earth we're talking about this in the first place. And don't worry, as always, it will come together a little bit later. Rest assured that I'm not just teaching you this to wow you with technical knowledge or anything like that. There is very real purpose to this. And I also know that understanding the difference between the luminance histogram and these other ones can be a little bit complicated. So let's just try a quick mental exercise. Yes? No question.
I'm not just trying to track this. So if there was no green or blue,
Yes.
would that entire box be red? If there was no green or blue in this area?
If there was no green or blue, would the entire box, in which portion?
Like the photo, the big box over here, would this all be red?
Would this all be red if there were no green and if there was no green and no blue in the picture? Yes, that's correct. And in fact, you see that here, what we're doing with this, these 3 histograms is we're breaking it down into what are called channels. So we have a red channel, we have a green channel, and we have a blue channel. And we can actually open this sort of thing up in Photoshop. It's usually associated with layers. It's the tab right next to that. And you can usually select one of these channels and see only that channel, and they convert that channel to black to white. That's not a luminance conversion. They're just showing you the black values are, the complete absence of that color. So if we're looking at the blue channel, for example, we can imagine that the blue channel would look like black to white, because there's a complete absence of blue on this side, there's the complete presence of blue on this side, and it's this gradient as we go from left to right. And we'll be talking about channels when we're probably in the next lecture when we go into more software tools. But as a mental exercise, let's think about what would happen if we changed this gradient a little bit. So rather than a gradient of red to white, how would each of these histograms, and first let's talk about the luminance histogram, how would each of these histograms change if it was a red to black? So it's the same thing, except instead of being white, it's a gradient of red all the way to black. So the luminance histogram is talking about the brightness, the apparent brightness of the image. So how would that look? Yeah, so it's basically the inverse of this. It starts at the very far left, and I can't quite reach it, and it goes about 30% of the way over. Now, how about the red channel? Be careful here. What will this look like? It doesn't look the same because if we go from red to black, remember, what is black? It's this total absence of a color.
Oh, would it just be the one, but on this far left side?
So it's also not on the far left side because there is some red in this photo. So it's basically, it looks like this green one, but it's in this red because we go from the complete presence and then through this gradient and then to the, or rather this complete presence, we go through the red values and then to the complete absence of red. And so what about the green channel? Well, there's no green at all because we're just going from red to black. We're not adding any extra colors. So we have a green channel histogram that's just one spike at the very far left. Blue channel is the same sort of thing. And in fact, during the break, I quickly made up that exact image. So we have here a histogram that goes from red all the way to black. And we have here the Photoshop window that shows us the histogram. So you can see this is the luminosity histogram that we determined. We can look at the red channel only, and it goes from completely black to completely red. Green channel, complete absence of it. Blue channel, complete absence of it. Now you'll notice that there's a couple other histograms that exist here as well. And so talking about these red, green, and blue channels is really meant to be sort of cursory because we do have these other, perhaps more important histograms that exist as well. So I would argue that these three are perhaps the three that you should really sort of know. You might use those red, those green, and the blue ones, but it's going to be pretty rare. And in fact, the majority of the time you'll be using the luminance histogram and possibly the RGB. Now sometimes your camera will allow you to choose other histograms, and that really is up to your camera. And one of the questions, in fact, on the assignment is to figure out, if your camera doesn't give you the option to figure out which histogram it is, one of the things you'll be tasked to do is to figure out which of these three types of histograms it might be. And in fact, I'll tell you right now that an easy way to tell with colors is that if you see a whole mess of colors like this, then it's probably a color histogram. But if it's just this sort of black and white version, it's RGB. Now, one of the things that I want you to notice about this colors histogram is that it really is just sort of this combination of these three individual colors channels. So it's superimposing one on top of the other and actually adding those two. So it's actually adding the colors together and showing you this colors one. So it looks confusing because it's this cyan, and so you have to sort of know that cyan is this combination of green and blue, and so it gets to be a little bit confusing, I think. So colors, it's pretty useful, I think, only when you have photographs. Then you'll actually see different humps. For example, you see like a red hump here and a blue hump there, for example. Then you'll be able to know where the majority of the colors are that exist in your photograph. And the RGB one is more like an average of those three. So we have the red, the green, and the blue channels, and it's combining them and averaging them in some way. Oops, forgot the blue one. And it's putting them into this black and white version that we're calling this RGB histogram. So what's important to realize is that for this same photo, the same image, we have essentially two completely different histograms. We have a luminance histogram where there's this big gaping hole about 30% of the way in. Then we have an RGB histogram that actually spans the entire width of the histogram itself. So this implies that there's some actual sort of difference, useful difference between these two types of histograms. And indeed there is. Luminance histograms are quite useful for showing you the apparent brightness of an image. But it's not very good at telling you when you're completely overexposing one particular color channel. So we've been talking about these unique color channels, this red, this green, and the blue, and the same sort of thing exists on a very physical sense in your digital camera. And of course, I have to hand wave and say we'll be talking more about this later, but you actually have this concept of red and green and blue channels in your digital camera, and it's possible that you can overexpose one of those channels. Maybe not the whole thing. So before we've been talking about overexposure in terms of this pure white, where it becomes completely white and you lose all of the data in that white spot. But the same thing can happen to individual color channels as well. And for those of you that love to take photos of flowers, for example, you're particularly prone to this, particularly when you're taking photos of red flowers, for instance. If you oversaturate it, you will get an underexposed image, but there's so much red in there that it will actually blow out that color channel. You lose this information. So it's this complete red in the flower itself, but what you've lost is the detail within that flower. You just have this blob of color. And yeah, it looks really nice because it's this big blob of color, but there's no detail. You've lost the texture in that flower itself. So the luminance histogram is good for showing us apparent brightness, but it's not good for showing us when we've blown one of the individual color channels. That is what the RGB one is useful for. You'll notice that here we have this big spike in the upper end of the histogram. We can see that we're somehow overexposing this image, and that is with the red color channel itself. And to give you so I have to give you another ugly image, but bear with me for a moment. To give you an idea of this, let's say we have an image like this. So yes, this is abstract, but it's meant to show us a point. The point of this is that we have a lot of colors. We have red, green, and blue colors, but we don't have a lot of brightness change, really. There's no really white areas in this photo. There's no really very dark, very black areas in this area, or rather in this photo. So our luminance histogram reflects that. We see that there's 0 pixels in sort of this very bright upper region, and there's 0 pixels in this very dark lower region, but we can see that we have these spikes of blue, of red, of green, where we have, each of these individual sections of color. Now, keep in mind that your photograph will not look as blobular as this, and so you're not actually going to get very nice spikes with a luminosity histogram like 30% of the way in or 60% of the way in. It's more likely going to be a bit smoother, but this is just meant to show this one aspect of the histogram. Yes?
So if in the luminosity histogram, if blue is the color that there's the most of,
Yes.
that's the value that peaks, it'll just peak all the way to the top?
Yes.
All the other ones are relative to their proportion to that, so their peaks will be...
Right, that's correct. So if you have in a histogram a peak that goes to the very top of the graph, everything else is relative to that particular peak. So you could say that, okay, well, there's a lot of very red pixels, but it looks like there's only maybe like 80% of the number of blue pixels. And sure, green is brighter, that's why it's up to the right over here, but it's only like 30%. There's only 30% of really green pixels. And we can sort of see that in the image as well. There's less green than there is blue and red as well. So yes, it is a relative thing. The graph is always relative to itself everywhere else, if that makes sense. So even here, so this low point is relative to the very high point that exists. It doesn't sort of go off the chart, so to speak, but you can think of it that way if you want. Okay, but the RGB what's nice about the RGB one here, and so this is an image that actually shows you the difference between what these histograms are measuring very, very well. Because here, the apparent brightness of the image, there's nothing that's, it's very, very dark. There's no very dark shadow region, and there's no very, very bright highlight region in this image. So that's why we get this particular luminosity histogram. However, we do have this very wide array of actual color information. So we go from some sections where, as you can see in this blue section, there's no red, there's no green, there's only pure blue. And then there's other sections that are that pure color, and there's pretty much everything in between, all these gradients between the red, the green, and the blue. And so we get this RGB histogram. So there's some areas where there's a complete absence of red, a complete absence of blue, complete absence of green, and combinations thereof. But there's also regions where we have the complete presence of each of these colors. However, we don't actually vary that much in terms of the actual brightness of the image. And so we can see, using the RGB histogram, regions where there's just no more detail. So we can imagine that if you remember going back to this sort of dynamic range that we were talking of. So we had this dynamic range and we had this tonal range. So we'd have a pretty good tonal range in this image because you can see kind of smooth gradients between each of these, these very, very bright regions of color. But because these gradients stop and all of a sudden it's just this pure color, you can see that the dynamic range of this quote-unquote scene is actually larger than that of what our image is capable of taking. So to make this become a little bit more concrete, imagine that we have something like this. So this is something that I alluded to earlier. If you take pictures of flowers, which can be very, very pretty, you can actually very quickly overexpose certain channels of color within that particular image. And I want to make this clear to you. So I'll try to zoom in. And if we look at the detail that exists within some of these flowers, you can see that, sure, you see the shape of the flower, and here you can see some of the detail, but in some of these very bright regions, you've lost the detail in that flower. So yes, it looks bright, and yes, in this case, it looks properly exposed, but we've actually lost some of the detail that's most important to this photograph, the actual flowers themselves. So this is something that you have to be watchful for. And this is a perfect example of how these different histograms can help us. So if we look at the luminosity histogram, it's just, we have sort of a big peak here in the left-ish end, and that's because for the most part, it's not a very super bright image. It's not like an image, if you imagine in your mind's eye, an image of pure snow, for example, which would be sort of glaringly bright. This is much more mellow than that, and it's reflected in the luminosity histogram. However, we don't see in the luminosity histogram the fact that we have blown out those particular colors in this image, that we have lost information in this image due to blowing out some of this color information. Yes?
So, I mean, because that exact same situation happened to me where it was very brilliant red flower, so brilliant yellow sunflower.
Mm-hmm.
How would you I mean, because the rest of the photos is so how would you compensate for that without then going to the point of underexposure in other areas?
It's a complicated thing to try to solve. So if we're trying to solve this problem where we're still trying to keep the image as a whole properly exposed but not blowing out one of the color channels, I mean, we have a couple of options available to us. We could use that bracketing technique that I was talking about from earlier, where we take multiple exposures and then we find the exposure that as a whole it will be dark, but that has the most color information here. Then we can try to add it back into this properly exposed photograph. That will actually result in perhaps a slightly awkward looking photograph. It won't look very natural, in other words, just because we have this perception of what this photograph should look like, and if it suddenly looks very, very dim in very specific regions, if it has very, very low contrast in just very specific regions, we'll sort of detect that and maybe not explicitly, but we'll be able to think, oh, something looks off about this photograph. So another thing you could do is to try to lower the contrast or try to lower the saturation. And sometimes, if you were lucky, you might be able to recover some of the data back. Of course, the downside to that is that it just doesn't look as punchy. There's not as much color there. There's not as much of that good look. So there's not a lot of options that, there's no good option that we really have. Another thing you could try, I guess, would be to somehow alter the light in this scene so that, for example, let's see, you could try, you could try putting this section of flowers under a bit of shade, for example, and then because there will be less light there, you might be able to recover some of the details. But of course, it will be a little bit darker. It's a complicated problem, and unfortunately, there's no perfect solution. Pretty much anything that's going to recover that data is going to make it look a little bit darker, a little bit less contrasty, or some variation thereof. Or you could try, if you really wanted to go artistic, you could do that spot color technique where people they take only the color they want and then they make everything else black and white. It's a masking technique that we'll talk about masking later, but you could do something like that, which is cheating perhaps, but then when you only isolate that one color, then you could have all the gradations in it and the texture, and you're not changing its apparent saturation, if that makes sense. So it'll look saturated relative to that gray scene surrounding it, but it may not be as saturated as it would be in this particular case. So I'm doing a lot of talking, and basically I don't think there's a perfect option. It's just something that we have to try to combat using a variety of techniques. Yes?
I'm wondering if you were trying to fix this in the field rather than in post, would there be some type of filter that you could use to maybe keep out a little bit of the red while not affecting the green areas?
No, indeed, you could certainly use a color filter to try to filter out some of the color that exists in the scene. So if you didn't want to do, just to repeat for the camera, if you didn't want to do a lot of post-production, so you take this image into Photoshop and you don't want to manipulate it a lot there, then you could use a color filter, but there's a couple problems with that. First of all, you have to know color filters and you have to know which color filter to use, but then you will still have sort of the same effect where you were altering the amount of color in the scene and it will change the apparent saturation of it. I think, let's see, so it will even change the relative saturation if you use like a, let's see, which one would it be? It might be a green filter to try to reduce the amount of red in it. Then you could, is that right? A cyan filter to reduce the amount of red in it. Then it would just, I think that would just make the flowers look very subdued in terms of their color, which sort of arguably destroys the point of the picture, which I think is the contrast in the color between the flowers and the green surrounding it. I guess another option you could use is a neutral density filter, but when I talked about neutral density filters before, I don't think I mentioned the graduated neutral density filters, which is basically, it's just like a gradient where it's completely transparent at one end and then it's completely dark, well not completely, but some level of dark at the other end. And they have graduated filters for various colors as well. And you might be able to pull something like that off as well. Rather than actually putting it under shade, you could reduce the amount of light physically entering into your lens, especially down here, and then progressively have more light. So it's messy. It's not an easy problem to solve, in other words. So, okay. But coming back to the point of this, using the histograms, you can see that with luminosity, there's not a lot of indication that you've blown out that particular color channel. And I guarantee that when you're looking at this photo on your tiny digital camera screen, that's not going to be very apparent. What's going to be apparent is the contrast in the scene, that you've properly exposed it, and not the small little details that exist. So it's going to be something that's very easy to miss unless you look at these histograms. But if you take a look at the RGB one, you will actually be able to see, and it's difficult, but you can actually see a bit of a blip where you have actually overexposed a little bit of a particular color channel. And if you're lucky enough to have a camera that supports individual color channels, then you could actually see the red color channel individually, and you'll be able to see a very noticeable amount of clipping, as it's called. So there's too much information on this end, and so that's indicating to you that it's just too bright for the dynamic range of this particular camera. So it's easy to blow out colors, is basically what I'm trying to tell you. And using these histograms, you can try to figure out what has gone wrong and maybe be able to try to do something about it. So in the camera, you could just try to decrease the amount of exposure compensation. So if you go into negative exposure compensation, you could decrease the apparent brightness of that particular image. Okay. Now, when we are talking about histograms, we've been talking about the frequency of brightness, and especially as it relates to luminosity histograms within a particular image. And so one of the things that we haven't really talked about up until this point is, how does a camera know what black and white are? So how does it know what values are black and what values are white? And we sort of alluded to this earlier when I said that there's this specific range that the camera is capable of capturing. Above that range, it's going to look completely white, and below that range, it's going to look completely dark. And so this camera may not have a concept of black and white, but just anything sort of beyond that range is going to automatically look to be black or white. And so that is what we're talking about when we're referring to this dynamic range. Now, if we actually had a look at this same scene, if we were each of us present at this particular scene, it would not look like this to us, because our eyes actually have this very wide dynamic range within it. And so we have, thanks to our eye, a variety of things that happen. So so first of all, we have the iris, for example, which it's able to open and close dynamically and very, very quickly. So as we look across the scene, it can actually open and close to try to vary the amount of light that's entering into the eye. Our brain, in fact, will play tricks on us as well. There's a lot that's going on in the visual processing that is altering our perception of the brightness of the colors of the scene that actually exists in front of us. And our eyes can actually deceive us. And this makes it, though we're used to it, this actually makes photography somewhat difficult, because our eyes are very, very dynamic. Our eyes would see this scene without so much of a problem. But unless you're somehow conscious of the actual range in brightness between this dark area and this light area, you're not going to know that your camera is not capable of the same dynamism. It's not capable of adjusting itself as much as we are. Well, it perhaps is, but just not on the same photograph. So one scene as we see it is not the same as one scene as a photograph sees it. So as you know, that we have this, we can see varying levels of stops. And just to give you an idea, we are able to see the dynamic range of our eyes overall. So the amount of light that we're able to see in the darkest room versus the amount of light that we're able to see on the brightest day is about 1 billion to 1, or about 30 stops of change. And so that's, a billion times change in intensity is quite a bit. And the instantaneous dynamic range of the eye. So in other words, as we're actually looking at one particular object versus going outside and letting our eyes readjust, as we're looking at one particular subject, we actually have about 10,000 to 1 change or range in the brightness of something. So that's about 13 stops. That's in a bright day. When we're outside and it's bright and it's sunny, we can actually see about 13 stop change from the darkest areas to the lightest areas and still be able to perceive details. When we go into the dark, our range actually expands a bit. We get about 1 million to 1 dynamic range, or about 20 stops of change. So the dynamic range of our eyes changes based on how bright it is outside a variety of factors. But what this should tell you is that we have a lot of stops of dynamic range, our eyes, instantaneously in one particular scene. And as you can guess, cameras don't have this same dynamic range. It's much more difficult for cameras. And so when we're talking about dynamic range of digital cameras, I like to use an analogy of a bucket. So imagine that we have millions of these little pixels or buckets within a digital camera. So as you know, we have 8 megapixels, 12 megapixels, however many megapixels your camera has that many million of these little pixel buckets. And these buckets collect light. And in this analogy, you can think of it as rainwater. So as rain falls onto these buckets, we're collecting the rain, and then after we're done, we measure the amount of rain in each of these buckets, and then that helps us figure out how much light there actually is. So as photons come in, it fills this bucket with collected light. And there's sort of a minimum amount. So as you can imagine, if you actually have a bucket that's outside and it rained a little bit, and you go outside with the ruler and you try to measure it, and if it didn't rain enough, you're not going to get a very accurate measurement, right? You'll know that it's very small, but you just don't know how small it actually is. Maybe it was like 1/8 of an inch or 1/16 of an inch. Maybe your ruler just doesn't have that sort of resolution. The same sort of thing happens to us here in this bucket. And in fact, at the opposite end, let's imagine that it was like yesterday when it was snowing like crazy and we have a little tiny bucket, and all of a sudden this bucket overflows because there was just too much of this rain that fell. You can imagine that now we can't measure how much rain there actually was. There was too much for us to measure because it spilled over, and we know that it spilled over, but we just don't know by how much. And so this is the same sort of thing that happens in the camera. So we have a maximum amount of light that we can collect. We have a minimum amount of light that we can collect. And we can figure out what the dynamic range of our camera is just by using a very simple equation. We can figure out what the most amount is, so the quantity of a full bucket, and divide it by the quantity of the smallest bucket that we can measure, or the smallest detectable signal. So if there's too much rain, the bucket's overflowing, it's not readable. You know it's over full, but you don't know by how much. And in fact, if you'll let me take this analogy a little bit farther than I probably should, imagine you had all of these buckets that are right next to each other, they're very, very close, and you have one bucket that fills up very quickly and it spills over. It's going to also spill over into the neighboring buckets as well. So if you're really bad and you really overexpose a particular image, one of the things that can happen is this effect called blooming, where you have photons that almost literally spill over into the subsequent pixels, and it actually expands this region of overexposure to be a little bit brighter than it was in the scene. Yes? Yes, blooming also happened with film, but it's, I don't know if it's the same sort of thing. I imagine that it's on a very high level, it's the same sort of idea, but that's much more of a chemical reaction versus an electrical change. And so the concept is very different, but a similar thing did happen, yes. Okay, so we have this equation then. We can figure out exactly how much, if we actually knew sort of the raw data of the sensor, we could figure out how much dynamic range our cameras have. And in fact, a lot of times, this same data is available to us. Just when we're looking at the spec sheet of a digital camera, we can figure out, without having to do any math, in fact, they just give us the data, how much dynamic range our camera actually has. And believe it or not, for modern SLRs, for modern digital SLRs, we can actually get between maybe 10, maybe 12 stops of dynamic range. And compact digital cameras, just by nature of the size of their sensors and a variety of other reasons that we'll talk about later, they actually have many fewer stops. Sometimes it's 5 to 6. Now they're creeping up. As technology matures, it's getting a little bit better. We might be up to maybe about 7 or 8 stops of dynamic range now in each of these cameras. And so you can imagine that, that this is not that this is one of the reasons that this is a bad thing for us is that our eyes are capable of maybe a 13-stop change instantaneously, so we can see, we could have seen all these details that exist here, but the camera simply is not capable of recording that particular information. And so I have a question for you then. So why might digital SLRs have a little bit better dynamic range than compact cameras? Think of our rain bucket as an analogy. SLRs are typically bigger. Sensors might be bigger, so yeah, so we might have a bigger bucket. So we might be able to collect more rainwater then, so to speak, and we might be able to, we would then be able to collect more rainwater, so then we could have a better dynamic range. And that's just one of the reasons. There's a variety of other reasons as well, but that's certainly one of the things. And so with all of this in mind, I bid you farewell. So until next time, when we talk about more software tools, thank you for coming and bearing with me with the histogram, and have fun with your digital photos.